Good. We are doing some taping. Yeah, okay, welcome people who are across the street changing the world. We are, I should probably pull this up. Good. We have gone over the polynomials test, and we have gotten out this packet, or this worksheet called More Combination Trig Graphs. Let's do this one right now, number 4. I have pretty high standards for these being accurate and everything, because I did give you like dots and stuff. Andrew, can you move the mouse? It's going to drive me crazy. So fact, I don't know if this is going to come through in the video or not. Can someone roughly monitor that to make sure it's like in frame at all and stuff? So what can I say about 2 to the maybe I should do flat. What can I say about 2 to the negative x over 4? Well, it's definitely always positive because it's an exponential function. So cosine pi x is always between -1 and 1. That's just like a fact. And if I multiply through by 2 to the negative x over 4, then I find that this graph always lies between -2 to the negative x over 4 and 2 to the negative x over 4. Okay. Well, what does 2 to the negative x over 4 look like anyway? Well, it's an exponential function. The negative tells me that it's flipped over the y-axis, so it's going to be a decaying exponential function, and the 4 means it's going to be stretched out by a factor of 4. So I can kind of point plot my way to a nice graph of this. If I plug in 0, I'll get 1, of course. If I plug in 4, I will get, If I plug in 4, I get 2 to the negative 1, which is a half. And if I plug in 8, I'll get like a fourth. Agree? Yeah, that's right. If I plug in -4, then I will get 2 to the 1, which is 2. And if I plug in -8, then I will get 2 to the 2, which is 4. Alright, so it's possible with the dots and with the choice of window and stuff to get a pretty accurate graph of 2 to the negative x over 4. And then also -2 to the negative x over 4 is just the reflection of that. Oh yes. So much graphing. Haha. Okay, so this is the envelope for my function. It must lie in between these lines. Furthermore, cosine pi x has a period of what? 2. Yeah, that's true. The graph itself then is going to be like cosine, right? So when's cosine 0? At the halves, cosine will be 0, I guess, right? Can I get that purple?
Which one or two?
Just either one? The best one?
Bro. I don't know which one's better.
Yeah, I know, that's why I was okay, so, so if I plug in a half, I guess, then that will give me cosine pi, which is 0. So, and then as the period is 2, this function, I think I'm doing this right?
Yeah.
Yeah, is going to continue having roots at every half an integer point. All right. Also, when I plug in 1, I get cosine pi, which is -1. So that's going to be -1 times this function. So I'm going to end up down here. And when I plug in 0, I get cosine 0, which is 1, so I'm going to end up here. So now I think that this is just going to keep bouncing back and forth like this. Cool? Are we basically good? Yeah. So this is actually like a semi-common thing that happens in science. Can anyone think what's like a thing that might behave this way?
Sound.
Yeah, like sound. Can you elaborate?
For sound waves.
E waves.
Wait, can you like elaborate with a little bit more of the like physics explanation of what's
Amplitude.
Stuff moves, yo.
stuff moves? Yeah, okay. No more. It's like, yeah, you have some sound, and what's happening to the sound?
It's fading.
It's fading. Yeah, this is like this is called a dampened. I think this is called like a dampened sine curve. And yeah. Well, something like that. All right, are we good? Say good. Good. Then we shall. Where'd the cap of this marker go? Oh man.
Are you holding it?
So,
Right there. Wait.
good, can you grab it? Thanks. Good, go to the back. The back is really hard. And also, Kelly, can you also erase that thing? Justin, are you keeping things like in frame and stuff? Yeah. You keeping an eye on that?
That's good.
So yes.
Right? That's looking at.
No, wait, so you see.
Alright.
Does that suggest?
So, this is sort of awkwardly placed, so that I'm not gonna get how much I want. Is that better or worse? It's like, ugh. I'm so upset. Alright. How about now? I guess we'll just talk it out. Alright, this doesn't really work on my system. Maybe I'll just make the chart somewhere else. Yeah, that's what I'll do. Wait, what's up? Okay, well, you should get a copy now. It's somewhere in this bottom cubby hole. Find one. All right, so this problem, this is an excellent combination of all the things that we had been learning up to this point. This is the graph of x sine 1 over x. Okay. Well, first I made this kind of like weird chart which you sort of saw before. I'm gonna have to just like reproduce it on the board because the screen isn't cooperating. -2 over pi, -1 over pi. Am I doing that right? Yeah. -1 over 2 pi, 0, 1 over 2 pi, 1 over pi, 2 over pi, 3 over pi, and 6 over pi. Okay, so those were like roughly the points that I recommended you take a look at. And then I said, what is x roughly for these points, and what is the sine of, is that just the function? See this? X sine 1 over x, yeah. So, okay, well, let's just, maybe we just should just start listing the properties of this function. So go, what are some properties of this function? F of x equals x sine 1 over x. Justin, you're keeping me in frame?
He is now.
Okay, good. Properties. Go faster.
It's like
It is even, in fact, because it is the product of two odd functions. So that's good. I very much agree. More.
It has a domain of all real numbers.
Yeah, just about. Yeah, I can't plug in 0 in, but everything else is going to be fine. Okay, good. One is an asymptote. What kind of asymptote? A horizontal asymptote. So you're talking about end behavior over there? Yeah. Yeah, the Shrish is talking about end behavior. He wants to say that as x goes to infinity, x sine 1 over x goes to, what does it go to? 1. Is that true? This was actually almost like the only important really thing going on in the back here. Why? Where'd you get that from? Plug in infinity. Maybe we should do all this kind of minus point plotting first. So back over here, this is like about -2, this is about -1, this is like -2 thirds, -1 third, -1 sixth, roughly 1/6, 1/3, 2 thirds, about 1, about 2. And oh, actually, I feel like I don't want to do this chart because it's like annoying, right? Or wait, is it annoying? I can't remember.
Calculator.
It's not that hard? Okay, so wait, let's do it. If I plug in negative 6 over pi, then what do I get? I get sine of pi over negative pi over 6, which is negative a half times negative 2. So it's like pretty much almost 1.
Okay, I don't.
Yeah, so that's interesting. And then if I plug in negative 3 over pi, then that's sine of negative pi over 3, which is negative root 3 over 2.
Wait, negative pi over 6.
I'm on the next one now, right?
Yeah.
Yeah, so I think I'm doing this right. Negative pi over, sine of negative pi over 3 is negative root 3 over 2 times approximately negative 1. So that's approximately negative 3 over 2. Okay, now if I plug in negative 2 over pi, what do I get? Pi over 2, which is like 1. So it's like about, it's like negative 2/3-ish, right? Yo, what's up?
Shouldn't that be positive?
Probably, yeah. Should they all be positive?
Yeah.
Am I screwing up? Yeah, because I'm multiplying by negative 1. Yep, and then I'm multiplying, yeah, good, thank you. And then if I plug in negative 1 over pi, now I get just 0, right? No.
Yes.
Yeah.
Yeah.
Yeah, and this is 0, and this is undefined, so this is 0, and this is 0, and actually it's all even, so you're right, whoever cautioned me not to give up, thank you. Yeah, it was not too hard. So maybe we can plot this. Now, if I go to roughly negative 2, I get roughly 1-ish, a little bit less. Where's 1? Is that 1? I can't tell. Yeah. So almost like 1. And then if I go to negative pi, or negative 3 over pi approximately, it's like root 3 over 2 almost. And by the time I get to roughly here, it's like almost kind of like 2/3. And then by the time I get to negative 1 over pi, it's 0. And it's also 0 here, and also 0, and also we know it's even. Alright, so this is kind of interesting. It's related to that other crazy function that we graphed, but it has a little bit of a different action. The one thing that you guys didn't mention is, well, we can maybe mention them now, right? The roots. What are the roots?
Every x, when x equals pi, a multiple of pi.
Yeah, like a reciprocal of a multiple of pi, actually, right?
Yeah.
So yeah, that's right. If you give me anything of the form 1 over k pi, if you plug that into this function, then it will be 1 over k pi times the sine of 1 over k pi, which is k pi, which is 0. Okay. So, yeah. So basically that means that this guy, like our previous function, is going to have an infinite number of like roots and oscillations very, very close to the origin. So it's going to go crazy near the origin. But oh, there's another really important thing that we haven't mentioned yet, which is like super important. The envelope, yeah, the envelope is super important. Again, sine 1 over x is always between negative 1 and 1. So assuming x is positive for the moment, that tells me that x sine 1 over x is always between negative x and x. And then if x is negative, it like flips in the other direction. Okay, so a very important observation is this thing to scale? It's like not, right?
It is.
No, I mean like the x and y's are like different, so I have to just kind of like,
I think
but
it might be.
I think it's actually
X
like,
and Y
it's like
are the-
square, right, kind of? Does it appear to be roughly squarish? You know what I mean when I say square? Okay, good, anyway, good enough. Alright, so, putting together all the things we have learned, it is indeed even. It indeed has roots at every 1 over k pi. Indeed there is a y equals x and y equals negative x envelope. If you missed that, that's a pretty big thing to miss, right? Because that was like the whole thing that we did on the other packet over and over again. As this is the product of sine 1 over x and x, it's going to have an envelope of y equals x. So that sort of helps me feel what this curve is going to look like near the origin. It's going to kind of come down, and then it's going to go totally insane near the origin again, like sine 1 over x did, but it's going to go insane inside an envelope of y equals x and y equals negative x. I used to make a joke about like a straitjacket. It's like a crazy man in a straitjacket, but now all I think about is in terms of baby swaddling. You guys know about the whole swaddle the baby thing?
Yeah.
Yeah, just constantly wrapping my baby up in tight straitjacket like swaddles so she can calm down. That's what's happening to our insane sine 1 over x function. It's being swaddled by crazy baby. And then it's kind of going like this. Alright, so the only real mystery is what is happening as x goes to infinity. And I have 2 reasons to think that it's 1. Sharice told me, and also it looks like it. Can I get something a little bit better than that? Yo.
How does it go below the axis?
What?
How does it go below the axis?
The x-axis. Because if it's like
Because sine is negative sometimes?
but if you're always at just pi over 12 and you just keep going smaller. Wait, no, wait, because it's 1 over. Never mind.
Okay, cool. Yo, whoever.
If you plug in something like really
Just
big,
kind of try it. Or wait, sorry, I shouldn't cut you off. Keep going.
if you plug in something like really big, then it's the sine of 1 over something really big, which is just a really small number times a really big number. That's what it's from.
Okay, so that is just a unreliable borderline falsehood that you just said. He said that if you multiply something really, really big by something really, really little, it's 1.
But no, if you
Okay, good.
sine of a really small number is almost indistinguishable from the really small number.
Yeah.
So it works.
Okay, yeah, that's some good stuff. Recall that we graphed previously, multiple weeks ago, the function sine x over x, which had a whole other sort of thing to it in which there was an envelope of 1 over x, and it did this and stuff, and then we were like, oh man, what is happening at the, oh my god, and then it turned out that what was happening was it was going to 1. And why? That's because we made a big circle and we said, okay, if the x input to the sine function is really small, then the sine is almost basically the same thing, right? Can you guys see this tiny little picture? Justin, give me a hard zoom in over here.
How do you zoom in on this?
Yeah.
Right, it's the top one.
Okay, good. So the sine is indistinguishable from x when x is really, really, really small. Did that work? Good. Say yes.
Yeah.
And now zoom out. Alright, what Evan was just saying is a deep and important fact, which is that when x is very, very small, sine x is basically x. And if this is your takeaway from that activity, which it was supposed to be, then that sheds light on what's going on here. Because here, we're taking the sine of something really, really, really tiny, right? Because when x is really big. I'm still answering this question now. I'm answering the question, what happens as x goes to infinity? Sharice said it was 1, but let's pretend we don't believe him or don't understand why. Here's why. If x is really, 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 really big, then 1 over x is really, really, really small. But if 1 over x is really, really small, then sine of 1 over x is basically 1 over x. Follow? When 1 over x is really small, which it is as x goes to infinity. And so this function is looking more and more like x times 1 over x, and indeed the end behavior is 1, and Sharice was right. So alright, cool. This is a very interesting function with a sort of infinite oscillations which are constrained by y equals x and y equals negative x, and also this horizontal asymptote of y equals 1. Alright, inequalities package. Grab that guy, please. Can you flip the camera around to that board? Alright, so we did, or you did, pages 1 through 4 of this inequalities packet already, I think? 1 through 3?
Yeah.
Okay, good. Let's do page 4 right now. It's pretty straightforward. I will provide minimal guidance.
You can do it.
Number 7, just do it. That's just straight up algebra 1.
There are like two cases. Wait. On the inequality. Is this the inequalities review? This one? Four.
It's not less than 8 and less than
Should you turn the lights back on?
Did you say pages 4 and 5?
Just number 7, go. People who are confused, look around and do what everyone else is doing.
Between 2 and 8, yeah.
No, I did this.
Number 8. What do you feel like doing?
squaring, but I'm
Squaring.
not too quick down.
Yeah, no, I think it's okay, right? Because when can you square both sides of an inequality?
All the time. But when they're both positive.
Yeah, when they're both positive. It is a fact, which can be proven, but I don't feel like it, that if you have, or maybe I do feel like it, if A is less than B, and A and B are both positive, then it is legitimate to conclude that A squared is less than B squared. Proof upon demand. You would have to go into some like very low level properties of inequalities to prove this, but yeah, it can be done. Right. Yeah. Good. Good. So number 8. Surely this is like a compound inequality in which. Well, of course, root x is positive. These are all positive, so just boom square. X is between 9 and 100. Good? Okay, next. Number 9. What now seems like tempting?
Multiply by x.
-1.
Yeah, it seems tempting to like reciprocate or something. Is that legit?
Yeah.
You can just multiply by x.
To the power like
Let's do some examples. 2 is less than 3. What is the relationship between 1/2 and 1/3?
Oh god.
It's not
There's
true.
flips.
It's just
the sign
flips, yeah.
flips. Oh, the sign was there.
1/2 bigger than 1/3. Does everyone agree that that's like just correct logic? Good. All right, next. How about if they're both negative? How about like the fact that -3 is less than -2, which is a true fact? What is the relationship between -1/3 and -1/2?
Yeah.
-3 is greater than.
It is. All right. What is the cool? Everyone cool with this?
Yes.
All right. How about what if I do like -3 is less than 2? What is now the relationship between -1/3 and 1/2?
Keep
What?
the
-1/3.
Yeah. I mean, this one's kind of just like a duh. Every negative number is less than every positive number. So the moral of the story is, if you have an inequality where both numbers are positive, then reciprocating flips the sign. If you have an inequality where both numbers are negative, reciprocating flips the sign. And if you have an inequality where one's negative and one's positive, then just like duh, right? Of course, reciprocating will keep the sign, but like yeah, because like every negative number is less than everything. Follow?
Follow.
All right, so right away you can now do 9, 10, 11, and maybe 12. Go.
Did we do 7 yet? Or
7's algebra 1. Wasn't that was on there for you? I will let it pass without comment, unless you would like me to talk about it.
no, I was just wondering if like goes on.
So number 9, what do you want to do right away?
Multiply by x.
Multiply by x. See, I don't want to multiply by x because that's kind of what I don't want to do, right? Because I don't. Well,
You can split into 2 inequalities.
It does work, but it just.
it does work, but I think this is simpler because look, I know that 1 over I know that x is positive in this case. Why do I know that?
Because it's between.
Because yeah, 1 over x is between 3 and 9, so 1 over x is positive, so x is positive. So all 3 of these are positive. If all 3 of these are positive, just reciprocate, boom, and then flip the sign, and like we're just done, right? 1/3 greater than x, which is greater than 1/9. Answer, everything between 1/9 and 1/3. And then in 10, you can do 10 in multiple ways, I suppose.
I just multiply by x.
Otherwise you could.
But you can also.
Yeah, but then you have cases, whereas I think this is maybe pretty
Yeah,
alright.
when it's negative and positive, that's what I was worried about.
Right, but now I'm trying to tell you, maybe you don't have to worry, because here I can for sure know that 1 over x is negative, because it's between -2 and -7, and therefore, either you could multiply through by negative and flip the sign, or you could just reciprocate as is, right? You guys with me?
Yeah.
And, boom, something went wrong, no. it didn't. So it's everything from -1/2 to -7. Right, how about 11? What should we do now?
Multiply by
Make two equations.
Same thing, reciprocate.
No, I think we still don't, I think we can still be smooth with 11, right? Because I know that thing in the middle is positive. So I think I can safely reciprocate, then multiply through by a negative, then add 4. Anyway, I'm gonna assume people can do this. Alright, are you guys good? Say good.
Good.
Okay, good. 12 is much trickier. Why is 12 much trickier? Yeah, because you don't know whether x is negative or positive. There are many ways to do this, so I don't know. Good luck. I won't give any more tips on that. Alright, next page. Solving trigonometric inequalities. Very important skill. Alright, let's do one together. Number 14. Is this camera on me still? So sine x is positive. Yeah, I want to know when sine is positive. Well, okay, this is like pretty dumb. When is sine positive? Just loosely speaking, just like give me your first initial. 0 to pi says, got it. That is pretty much right. In fact, sine is the y coordinate, and or the yeah. So yeah, indeed, it will be positive. All of this stuff. It's nice to draw a little picture. All right. So in some sense, we're already done. As soon as you just draw the picture, you're kind of done. Okay, but you might want to be a little bit more picky about this because it's not just from 0 to pi. In fact, it's like
Plus 2 pi k.
like plus 2k pi or something like that. So it's like also going to be from like 2 pi to 3 pi and like et cetera, et cetera. So if you think about what's going on here, it is everything from 0 to pi, and it's everything from 2 pi to 3 pi. Are you with me? Waiting for like the type learning noises. Also, good. Also, it's like everything from like whatever. What is that? Negative 2 pi to negative pi. Is that even right? Yeah. And then like et cetera. Okay, so the actual solution to this problem is like an infinite union of intervals, or a union of an infinite number of intervals. You with me? It actually says all this right in the paper. So, how can you write this? Well, you can just be like, there's a bunch of ways you can be like, yo, x basically has to be between like a 2k pi and a pi plus 2k pi. So, let's write this, and now we use the fancy giant union symbol. It's the union of all intervals of the form 2k pi to 2k pi plus pi for every integer k. And you put the like index or something like under the u. Are you guys like roughly okay with that? I feel like that was a pretty decent explanation. Yo.
If it were inclusive, would you use square bracket?
Yup, you would. Okay, go. Do some more. Right now, do 17. Which is kind of hard. Maybe 16, 17, 19, and 22. Maybe right now. Go. Oh, and people watching at home, this is the inequalities packet. You should like do it also. All right. This is gonna be a really crappy YouTube video. I'm gonna like delete it soon. soon as they watch
You can
it.
make it unlisted.
I'm just kind of tired.
Give them the link.
You're gonna become YouTube famous.
Where, I don't think I'm going to become
Where's Sine?
anytime soon.
Or 16. I feel like the big union of this equation. There's like two disconnected things, right? That union, that, and then the big union. Yeah, this is. I think 17. It's like 19, but I don't know.
Wait, no, this is just like two things, right? Because it's just the first quadrant and the third
The
quadrant.
point of the union.
But I didn't. How do you use the big union symbol?
Yeah, this is the same formula. So for like any like if you're going all the way to 10 pi, then you would just put in 10.
Oh, you did solve it.
So bad.
Oh, yeah. All the union two unions, I guess.
Oh, did you just figure it out?
Instead of those two pi.
And then you just change it up based on.
But I mean, how did you learn how to do it? You just use common sense? What's up with you?
And then
Just
find
doing
everything
it.
out. Yeah. Yes.
And you want a closed one on the 0 and an open
Oh,
one.
okay. I thought it was like an outside.
Oh,
Alright, my bad, my bad.
It might be
So this is the lower bound, and then this
or no, it's not.
is. So if you look at this, it's when it's 0 to 5.
0 over 1.
And then 2 pi to 3 pi. So like you're always staying in that upper half of the circle.
No,
This is 0.
So
Yeah, that's zero, right?
this just relates to this one.
Yeah.
Greater than or equal to zero.
Yeah. Like they did it.
So wait, we're doing 16. Okay. I was gonna say. So if you know that it'll always be in this range,
Wait, this is just like
then you pay two
pi
different
over
steps. Right.
2.
So if it's 0 to pi, then you would have pi
Wait, no,
k
it gets
from
negative.
negative.
So it's just pi over 4.
And then if it's pi over 2 to 3 pi over 2, then you would do
And
one side just 0 to 3 pi over 2. Yeah, pi.
Is it
Instead of
cosine
having instead of being a 2 pi.
Yeah, so I think the pictures are really important. Where is tan positive? Quadrants 1 and 3, yeah?
Yep.
Yeah. So when is that? Well, tan has a period of pi. So the smooth way to do this is to just be like, yo, it's just going to be from here to here, and then just repeating every pi. Did you guys figure that out?
Yep.
Yeah, so this is like everything of the form 2k pi to,
Why do we use 2k pi now? Why not 2 pi k?
oh yeah, I don't know, I've always done it that way. 2k pi to pi over 2, oh no, it should be pi k.
Yeah.
Sorry, yeah. So everything from k pi to pi over 2 plus k pi, I think will be a solution. Agree?
Yeah.
Just like check me on. Don't just take my word for it. Yeah, but I'm right.
Don't just say my word for it.
Everything from zoom to boom, 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 boom.
Don't ask.
Good.